Hello and welcome. This is videos for Shaughnessy's Math 30-2 class. Keeping in mind the basic disclaimer, make sure that you're attending class because we go through it in much more detail there. This is Exponents and Logs lesson 10. This is the first lesson where we start to look at the purpose of what we're doing, looking at the growth and decay. We've explored all these exponential relationships, these logarithmic relationships, now trying to use it for something, so that's what we're going on. So, in no particular order, growth and decay. Lots of things expand or grow or decay or reduce themselves in an exponential fashion. Okay, everything from computing power to financial stuff to radiations and radioactive cases, that sort of thing. And so we have to look at even like earthquakes, and we look at the various relationships. And so in many cases the log regression or the exponential equation is given to you, and that's where we're going to start. Okay, the hard part is going and creating your own, and that's usually from some sort of data to say, hey, this is growing at this rate, here's an equation that models it. That's something different. Right now we're just looking at ones where it's given to you. Okay, so if I look at this one here, example, the value of a particular painting is shown in the graph below. Now what I'm going to do is I'm just going to randomly draw a graph. So I apologize if this isn't terribly neat, but I've got the value and I've got the age of the painting. Okay, and I've got 1-year-old, 2-year-old, 3-year-old, 4-year-old, 5-year-old, 6, 7, 8, 9, 10, and so on and so forth. I'm just going to put 10 in there. And basically, if you were doing it from a graph, you'd have some sort of very formal graph, okay, going through. It wouldn't be just hand-drawn like this one, but the process is the same. So if I say this painting, I need to pick a value of it. I'm going to say $1,000, and then there's going to be $2,000, and then there's going to be 3 and 4 and 5, and so on and so forth. I'm just going to put the 4 and the 3 for the thousands, and so on and so forth. Now, along with this, there's going to be some sort of data that's going to determine this. So what I'm going to do is I am going to give you some data, and I'm going to tell you that to start with, it was worth about that much, about halfway. Okay, after 1 year, it was worth a little bit more, and you've got a series of a graph that kind of goes like this. Okay, and so this is an exponential graph. This is exponential growth. It's turning and heading straight up. It's not drawn too terribly well. For those of you that want to nitpick, it kind of starts to level off. Please just ignore that. But ladies and gentlemen, you've got that, and you'll have some series of dots. Okay, if I say here, that's about 3,1100. Okay, and I'm just making up some data, and this one is about 5,2000. Okay, and this one is going to be about 7, and I'm just making up these things. Okay, in a more particular sense, you'd have some sort of rationale. You'd have some more accurate points. I'm just randomly doing this. Now, from this exponential graph, you've got a relationship between the value of the painting and the age of the painting. Okay? Now, you can debate all you want about whether or not this is a legitimate way of doing things, because in theory, a 50-year-old painting is going to be worth lots of money. Sometimes it is, sometimes it isn't, that sort of thing. So there's all sorts of stuff that could affect this. But using this model for this particular one, estimate the number of years it takes for the painting to be worth $5,000. Well, $5,000 is here. And so I can go across to the graph and say, okay, it's about that, and it's about there. So then I can count. Okay, that's my points, and I'm just using the graph to estimate. This isn't accurate, but I'm using the graph to estimate. And so 1, 2, 3, 4, 5, 6, 7, 8. So it's somewhere between a 7 and 8-year-old painting. This thing suddenly takes off. Now, why? I don't know. I'd have to look at all sorts of situations to really justify the rationale behind it. But based on this graph, I can say, estimate the number of years before the painting is worth $5,000. About 8 years. And it's just an estimate, okay? It's just an estimate based on this graph, okay? You've got this idea, that's it, we're done, okay? Now B, based on this graph, estimate the painting when it's 6 years old. Well, 6 years old is here. So 6 years old has that. And if I go across, it's a little more, it doesn't look terribly straight, but it's a little more than $3,000. And I'm using the graph just to estimate. This is going to be about, and I'm going to say $3,100, okay? Because it's an estimate. Okay, you could make a case that it's about 3,000, but you don't have any great accuracy to justify your answer. So nonetheless, that's there. But this is an exponential situation. And there's a whole variety of things, from values of cars to sound in decibels to all these things. They're exponential in nature, and so you can go with that. Now, specifically, this is exponential growth. Okay. And the reason it's exponential growth is because it's increasing in value. It's going up. The value, or whatever I'm talking about, is increasing. That's why it's growing. It's not that simple, or it's not that hard. Decay or exponential decay would be something else, like if you looked at the value of your new cell phone. Okay, as it gets older, it exponentially decays. It gets worth less and less and less and less and less, until after a year or two, the thing's virtually worthless. It's exponential decay, okay, and it goes down fairly quickly, and so on and so forth. This is growth. You can have decay as well. Some things like cars or computers, basically anything electronic, decays. A lot of things like investments or property grows, that sort of thing. So once you're comfortable with that idea that you've got, this exponential relationship, then what we can do is we can give you questions where we're talking about a particular topic or a particular context. We're going to give you the equations to start. So this one, the population of a particular town, P, after the year 2011, can be modeled by the equation shown below. Okay, so this is the equation. The population of the town is 5,308 times 1.035 to the power of x. Okay, so this is the year after 2011. So x is the number of years after 2011. A, determine the population of the town in 2011. There are two unknowns, P and X. And I've got to think, which one is it giving me? Now it wants to know the population, so that's the one I want. It's telling me X. Now figuring out X isn't always as simple as just looking at the number that's in the question, but nonetheless, it's just related. So it tells me that X is the years after 2011. If X is the years after 2011, and I want to know the population in 2011, X has to be 0. It's 0 years after 2011. So from there, then I can just take the equation, P equals 5,308 times 1.035 to the power of X, which is 0. And then I just evaluate this. Now there's a variety of ways to evaluate it. I could type it into the calculator. I could use the fact that anything to the power of 0 is 1. So all of this becomes 1. So I just end up with 5,308. And however you do it, you're going to get that. The population in 2011 was 5,308, based on this model. Okay? Now, this model is requiring, that you can assume that it continues on. Let's pretend that it's always growing at 3.5% per year. And if something changes, like if they discover that the town used to be used as a radioactive dump back in the 50s, all of a sudden this model isn't accurate anymore. But we're not worried about that right now. If this model continues, determine the population in the year 2022. Well, I have, once again, P and I have X. Those are my two variables. Population is what I want, so that's my question mark. I need to know X. Well, in the year 2022, how many years after 2011 is that? And I know 2012 is 1, 2013 is 2, 2014 is 3, 2015 is 4, and then you go through. And basically, when I take a look at this, 2022 is 11 years after. Okay. It's 11 years after 2022. Okay, so once I get that idea down, okay, then I've got to take and look, okay, what's this equation? So I can just go through and do the same thing. Okay, P is equal to 5,308 times 1.035 to the power of 11. Now I need to type this into my calculator, so I'm going to do that. And so I'm going to get 5,308 times 1.035 to the power of 11. And I work that out, and I'm going to get that the population of this town is 7,749.519 people. And you can say, well, how do I have 0.519 of a person? Well, you don't, okay? You just kind of round. The question often arises as to, how do you round, up or down? Basically, the premise is since this is an estimate based on a average relationship that I've been able to found, truly it doesn't matter too much. But so in class, or in math exams, basically in math class, we just follow normal rounding rules. So I need to know whole people. I look next door, it's 5, so it goes up. Okay, same rounding rules as before. So 7,750 people, about. Is it going to be exactly 7,750 people? It could, probably not. Okay, things change, et cetera, et cetera, et cetera. The model doesn't always hold. Now, C, determine the population in the town in the year 2012. Use it to determine the average annual percentage increase of the population. So, I want to figure out in 2012, and you may be thinking, well, we've done this before. X is 1, and I'm going to get the population is going to be 5,308 times 1.035 to the power of 1, and you can figure out that population. Okay. Now that population is going to be 5,308 times 1.035 to the power of 1. You end up being 5,493.78. Following the ordinary rounding rules, that's about 5,494 people. So, using from that, what's the average annual rate of increase? Well, how much percentage did it increase by in that 1 year to get to 5,494 from the 5,308 I had before? And so I say, well, what's the percentage increase? I want to find out what's the percent change. So I'm going to take 5,494 and divide it by 5,308. And this is going to be the percent change in that 1 year. And so the percent change, if I do that, 5,494 divided by 5,308 is going to give me 1.035 ... or more specifically 103.5%. So basically what this is telling me is after 1 year, the population was 103.5% of what it was before. The 100% is what I had before. 103.5% is what I have now. What did it increase by? 3.5%. I got 3.5% more. Now, for those of you that are looking, you're saying, Shaughnessy, why are you telling me this? When I look over here and I say, well, I'm multiplying by 1.035. There's my 103.5%. And I'm going to tell you that that's where it's coming from. That value there, the value that's in the exponent part, the base of this exponent, is the rate of change. So this is the rate of change. What this is telling me is each time you go past 1 year or past one period, it's going up to be, or it's going to be 103.5% of what it was before, or it's increasing by 3.5% per year. So you ask yourself, which one do you use? Do you use the mathematics and do all this work, or do you just justify? Truly, in all honesty, the answer is yours. However, your choice, but I would use this one. I would say right here, hey, I can see from here it's 3.5%, so why would I do the extra work? If you want to do the extra work, feel free, but I can see it right there. Okay? Going through using this idea, D, okay, and I'm running, it's a little bit cramped now, but D, based on the equation above, in what year was the population 10,000? Well, I have two unknowns, population and X. This time it wants to know year, and it's telling me the population of the town is 10,000. So I have the equation is P equals, but P is 10,000, equals 5,308 times 1.035 to the power of x. This is an exponential equation. We've solved lots of these. That coefficient, remember the coefficient can't be multiplied to that base till after I've done the exponent. Since I can't do the exponent, I can't do that multiplication, so I'm going to divide it off. So I'm going to get 10,000 divided by 5,308 equals 1.035 to the power of x. Then from there I've got to solve this. I'm going to solve this. You could take the log of both sides. I'm going to convert it to logarithmic form. So I'm going to end up with the log base 1.035 of 10,000 over 5,308 equals x. And all I got to do is figure out what this is. Because I have a newer version of the TI calculator, I'm just going to go in here. I'm going to clean out what's there. I'm going to go alpha, get the log base, and I'm going to type log base 1.035, and in here I'm going to put 10,000 divided by 5,308 and hit enter, and it's going to take 18.4 years. So x is 18.4 years. Whoops, not 1.8. 18.4 years. Okay, so what year? Well, it's going to be 18.4 years after 2011. So 18.4 years after 2011, it's going to be 2011 plus 18.4 years, which is going to be sometime in the year 2019. It's going to be sometime in the year 2019. I just go and say 18.4 years after 2011, add it. It's going to be about 2019. Okay, you don't need to say the 0.4 because the 0.4 just tells you you're about a little less than halfway through the year. So sometime in May or late April, early May, somewhere in there, you are going to be approximately 10,000 people. Now this is all requires this relationship holding, this 3.5% per year growth rate continuing. Now, obviously, if I'm saying that this is an equation, right now I have no reason to believe that it's not going to continue. All sorts of things could happen. The economy could take a downturn. This could be an oil town, and so suddenly now it grows faster, or suddenly now it goes slower. All of a sudden it could start decreasing. All of that stuff is possible. So if you want to say, well, I don't know if it's going to be 2019, the honest answer is no, you don't. You don't know it's 2019. You have no idea. You're guessing at the future. You're Nostradamus trying to make a prediction. But at the same point in time, based on this relationship, that's the best prediction I can make. Okay? Now going through, you can look at growth and decay. The value of a particular car, V, for years X after 2013 can be modeled by this equation. So I've got that. Okay? Determine the value of the year, the value of the car in the year 2015. Well, 2015, keep in mind, I've got two pieces of data, V and X. The value is what I want. 2015 is 2 years after 2013. So the value of this car is going to be 21,308 times 0.847 to the power of X, which is 2. And I crunch my numbers and I get this, 21,308 times 0.847 to the power of 2. Work that out. This car, based on this model, is $15,286.55. Okay. Is that dead on? Do I have to be that accurate? No. But based on this model, that's what it's predicting. Is it actually going to be $15,286? Well, there's absolutely no way to know. Okay, I could total it in 2014, and then it's not worth this. It's worth, the price of metal. I could have taken this, in 2014 or maybe in 2015 and put so much money into it and change the seats so that they're all leather and whatever else I could do, so that it's actually going to be higher than this. I could have left it in the garage so that it's got exactly 500 kilometers on it, so that means it's going to be worth a little bit more because it's low mileage. There's all these things that enter into it, okay? And once again, you're just predicting. You're just kind of thinking, well, based on this model, this is the approximate value, okay? So you could probably round it 15,287. You could round it to 15,300. Either way, that's done. Keep in mind, though, for the purposes of exams, just round it to whatever's reasonable, so the nearest percent, because that's how our dollar values work, recognizing, though, that it's an approximate. Okay. B, determine the average annual rate of decrease by calculating the car in 2016 and comparing it to your value in A. So once again, in 2016, I have the value, I don't know, I have the X. In 2016, it's 3 years afterwards. So I'm going to find the value. It's going to be 21,308 times 0.847 to the power of 3. And I go and figure that out. Okay, and it is going to tell me that the value of the car then is $12,947.708 or 71. So $12,947.71 based on this model. Now once again, it's an approximate. But based on this model, I've got that. What do I have? Well, you go look at the percentage, and some of you are saying, well, Shaughnessy, you said this number here. So instead of being 103.5% like it was in the last one, this one is 84.7%. So you can go through and say, well, what is the new value? It's the 12,947.71 divided by the 15,286.55. And these are rounded. So I get 12,947.71 divided by the 15,286.55, and I get 0.847, which is telling me that I keep 84.7% of my value. That's what I have after all is said and done. I have 84.7% of what it was. 84.7% of what it was. Just like before, I had 103.5% of what it was. Now I have 84.7% of what it was. So if I have 84.7% of what it was, how much did I lose? Okay. Because we don't say, well, I've still got 84.7% of my value. That's not really how the world works. Unfortunately, if I've got 84.7% of what I have or had, I lost something. What did I lose? The focus of humanity is on what have I lost? What has changed? So in this case, I had, 84.7%. So 100 minus 84.7 is 15.3. I lost 15.3%. I lost 15.3%. That is my rate of depreciation. Okay? Okay, I lost 15.3%. Now it was related to this. Okay, that number came out of there. But the thing is, I've lost 15.3%. Now, that's where this is going. This is exponential decay. And this is decay because it's going down in value. How do you know it's going down in value? It comes with this B value here, this value in here, sorry, it's called the B value, I'll get there later. This value in here, if it's less than 1, it's decaying, it's losing value. If it's more than 1, like it was in the last one, if it's more than 1, it's increasing. This is exponential growth. So more than 1 is growth, less than 1 is decay. Either way, it's going to tell you how much percent or what percent you have left after all is said and done. If it's more than 1, it went up by that much. Okay, the percentage that's hiding in there. If it's less than 1, it went down by that much. Going along with this idea, okay, when will the car have a value of less than or equal to $10,000? Well, keeping in mind with this equation, I've got two things. I've got value and I've got X. Here I want to know what year, so I want to know the X. the value is going to be 10,000. And basically anything a little bit later, it's going to be less because it's going down forever. Anything a little bit earlier is going to be a little more than $10,000. So I start with my equation. V is 10,000, and it equals to 21,308 times 0.847 to the power of x. Okay. So then I take this and I say, okay, I've got to do this. This is an exponential equation. Keep in mind you can't multiply these two together by the order of operations. So I'm going to divide by the 21,308. So I'm going to get 10,000 divided by 21,308. And that equals 0.847 to the power of x. Then from there I convert it to log form. So it's going to be the log base 0.847 of 10,000 over 21,308, and that equals x. I go and type that into my calculator. So I'm just going here, clear out what's there. Alpha window brings up that menu. Okay, I'm going to choose log base. Log of 0.847, and it's going to be, I'm just moving it over so I can see it, 10,000 divided by 21,308. Okay, and what is that? It's going to take 4.55 years, so x is going to be 4.5557 years. So I'm going to round this to 5 years. So basically, after this car is 5 years old, it's only going to be worth $10,000. Okay, now is that accurate? Once again, depends. It depends on this car, it depends on the situation. But based on this model, 5 years. That's how long it's going to take. A 5-year-old car, I'll give you 10 grand for it. That's it. Okay? I may have paid $21,000 a few years ago, but that's what it's going to be. Okay? And all that happens is you just look at various things. We're going to give you equations for all of these first. This one here, it's a chemistry context, but it's all exponential and logarithmic. The pH of a particular solution can be calculated using the pH equals the negative log of the concentration of hydronium ions. Okay, so you've got that. Concentration, square bracket, H3O positive, square bracket is the concentration of hydronium. The pH of a solution with the concentration of this. Now if you've taken chemistry, you've done this lots. You know that the equation is pH equals negative log the concentration of H3O positive. Okay, so there are two unknowns. One is pH, which I need to know, and the other is the concentration. And it tells me that concentration. It tells me that is 6.23 times 10 to the negative 8 moles per liter. Okay, so plugging that into the equation, I have pH equals negative log of 6.23 times 10 to the negative 8. Now, to type that into the calculator, I look at log here. What's that log? Well, that's what type of log is that? I can't see the base. I don't know what the base is. Well, that's a base 10 log, which is really nice because that's what the calculator does. So I have negative log of the concentration, which is 6.23 times 10 to the negative 8. Now, you can either do it like this, times 10 to the power of negative 8. I've got to get rid of that bracket because it's going to confuse the calculator. I can either type it like that, and the pH is 7.2, or negative log of 6.23, I had to look, times 10 to the, to get the times 10 to the, that's this capital E thing that's hiding right here above the comma. Okay, right above the 7 in there. That capital E. That's how the calculator thinks that. So I could go times 10 to the negative 8. Okay. Sorry, I paused that. Okay. But I could have 6.23 times 10 to the. That's what that capital E means, negative 8. Either way, it gives me the same thing, the 7.2055. So this pH is 7.2055. I'm just rounding it to the nearest tenth. Okay, 7.2. I didn't have to round it to the nearest tenth, I just chose to. Okay, so this is just an example. When we give you an equation, what can exponents and logs be used for? Okay, after X years, the percentage of a particular radioactive isotope remaining in a sample can be modeled by this equation: 100 times 0.5 to the power of X over 72. It doesn't show up very well on the screen. What percentage of the isotope remains after 26 years? Well, keep in mind, I've got the P, which is what it wants, and I've got the X years, okay, which is 26. So I know that I've got this equation with those two unknowns. I know X is 26, so I'm just going to start with the equation. P equals 100 times 0.5 to the power of 26 over 72. Now, all of it is in the exponent, okay? So I'm going to go type that in. And when I type that in, okay, I have 100, bracket 0.5, close bracket, to the exponent. If you have the new operating system, it's easy because it just shows up in the exponent as a power. Okay, so you're done. If you don't have the new operating system, you'd have to put 100, bracket 0.5, close bracket, to the power of, whoops, it's not going to show up because I got to do that. Here, give me 2 seconds. Mode, just to show you the new operating system, the classic. If you don't have it, you'll do 100, 0.5, close bracket, to the power of, open bracket, 26 over 72. That's what you'll have to do if you've got the older calculator. Either way, it gives you the same thing, 77.85 years. So, or sorry, that's the percentage that remains. 77.856% is remaining. So it's about 77.9%. Okay, that's how much is remaining after 26 years. Well, I don't know what this element is. I made it up. Okay, but nonetheless, all sorts of radioactive elements have these particular half-lives, and because of that, they have their particular equation. And in most cases, the shorter the half-life, the more radioactive it is, so the more problem it is. But nonetheless, you've got those sorts of ideas. You've got this radioactive element. Let's pretend I'm talking about some element that I have to have less than 20% of it remaining. That's when it becomes safe. So I look at this. Well, in this case, still keeping in mind I've got two unknowns, P and X. It wants to know how many years. The percentage remaining is 20. So I'm going to have P, or 20, equals 100 times 0.5 to the power of X over 72. Okay? Keeping in mind still, you can't multiply that exponent and that base together, so I'm going to divide it over. So I'm going to get 20 over 100 equals 0.5 to the power of X over 72. Now converting it to log form. This is going to be the log, base 0.5, of 20 over 100. That's going to equal X over 72. It's a little different than what we've been doing so far. X divided by 72 is going to equal this log. I want to know X, so I'm going to multiply by 72. That kills it here. But whatever I do to one side, I do to the other. So I'm going to get 72 times the log base 0.5 of this. Okay? So I go to my calculator, I turn it on, alpha this. That's how I get my log base. Okay? So it's going to be 72 times alpha this log base. And, oops. Okay, I'm going to turn this back on to the other notations. So I'm going to get 72 times alpha log base. It's log base 0.5 of 20 over 100. I get 167.17 years. So X is going to be 167.17 years. Okay. Now, depending on what this element is, if it needed to be less than 20% for it to be safe, then it would take 167 years before this particular land, this particular scenario, this particular situation was safe. Okay? Now, every radioactive element has that. But everything that's radioactive has, a particular half-life, so it's exponential growth or decay. In the half-life case, it's decay. Please make sure you take a look at that. The questions today are going to be giving you the equation so that you just have to kind of use it. A little bit later on, we're going to talk about building them, but for right now, it's just given to you. If you have any questions, just let me know.